In Chapter 18, we developed the concept of an electric field and show that these were created by stationary charges. In Chapter 21, we moved these charges at constant speed in a wire to produce currents, and these moving charges created magnetic fields. Now we want to bring electricity and magnetism full circle by taking charges and accelerating them. This produces something called an electromagnetic wave. We will see that an electromagnetic wave is a transverse wave composed of mutually orthogonal electric and magnetic fields that propagate out away from the accelerating charge at the speed of light. One simple way to create electromagnetic waves is to attach two straight metal wires to the terminals of an AC generator, which acts as a simple antenna. The potential difference between the terminals changes sinusoidally and has a period t. Part A of the figure shows that at the instant t equals 0 seconds, when there is no charge at the ends of either wire. Since there is no charge, there is no electric field at the point P, just to the right of the antenna. As time passes, the top wire becomes positively charged and the bottom wire negatively charged. 1/4 of a cycle later, the charges have attained their maximum values, as Part B of the drawing indicates. The corresponding electric field E at point P is represented by the red arrow and has increased to its maximum strength in the downward direction. Part B also shows that the electric field created at earlier times, see the black arrow in the picture, has not disappeared, but has moved to the right. Now, at distant points, the electric field of the charges is not felt immediately. Instead, the field is created first near the wires, and then, like the effect of a pebble dropped onto a pond, moves outward as a wave in all directions. Only the field moving to the right is shown in the picture for the sake of clarity. The fields produced earlier in this sequence, given by the black arrows, continue propagating toward the right. The electric field at point P reverses direction as the generator switches the charges from positive to negative in each end of the antenna. Thus, the motion of the charges along the antenna produces an electric field that oscillates up and down. However, charges moving along the antenna constitute a current, and this current, like all currents, produce a magnetic field. When the charges move up, the current is up, and the magnetic field produced to the right of the antenna points into the screen, as indicated by right-hand rule 2. When the positive charges move down the antenna, the downward directed current produces a magnetic field to the right of the antenna that points out of the screen. Thus, the motion of the charges along the antenna simultaneously produces a magnetic field that oscillates in and out of the screen. Thus, the electric and magnetic fields created by the antenna are mutually perpendicular and remain so as they move outward. Moreover, both fields are perpendicular to the direction of travel. These perpendicular electric and magnetic fields moving together constitute an electromagnetic wave, which is a transverse wave. The electric and magnetic fields decrease to 0 rapidly with increasing distance from the antenna. Therefore, they exist mainly near the antenna and together are called the near field. Electric and magnetic fields do form a wave at large distances from the antenna, however. These fields arise from an effect that is different from the one that produces the near field, and they are referred to as the radiation field. Faraday's law of induction provides part of the basis for the radiation field. As section 22.4 discussed, this law described the EMF, or potential difference, produced by a changing magnetic field. And, as section 19.4 explained, a potential difference can be related to an electric field. Thus, a changing magnetic field produces an electric field. The radiation field arises because the changing magnetic field creates an electric field that fluctuates in time, and this changing electric field creates the magnetic field, and so on. It was the great Scottish physicist James Clerk Maxwell who showed that these two fields fluctuating together could form a propagating electromagnetic wave. An electromagnetic wave, unlike a wave on a string or a sound wave, does not require a medium in which to propagate. Thus, electromagnetic waves can travel through a vacuum as well as a material substance, since electric and magnetic fields can exist in either one. Electromagnetic waves can be produced in situations that do not involve a wire antenna. In general, any electric charge that is accelerating emits an electromagnetic wave, whether the charge is inside a wire or not. In an alternating current, an electron oscillates in simple harmonic motion along the length of the wire, and is one example of an accelerating charge. All electromagnetic waves move through a vacuum at the same speed, and the symbol c is used to denote this value. This speed is called the speed of light in vacuum, and its value is 3 × 10⁸ meters per second. In air, electromagnetic waves travel at nearly the same speed as they do in a vacuum, but in general they move through a substance such as glass at a speed that is substantially less than the speed of light, as we will study in Chapter 26. The frequency of an electromagnetic wave is determined by the oscillation frequency of the electric charges at the source of the wave. In our previous figure, the wave frequency would be equal to the frequency of the AC generator. We'll see in the next section that electromagnetic waves exist with an enormous range of frequencies.